Hello, welcome to section 4.3, linearly independent sets and bases. Basically, in this section, we are going to identify and study the subsets that span a vector space V or a subspace H as efficiently as possible. So we will discuss linear independence defined in Rn, and that's going to be our key idea. So remember that the definition of linear independent sets from chapter 1 is a set of vectors in Rn that is linearly independent if the vector equation is equal to 0. So that means that there is only one trivial solution. So that means that x1 is equal to 0, x2 is equal to 0, so on and so forth, in order for this equation to equal 0. Now, if this is not the case, then the set is said to be linearly dependent. And that means that some of the weights are not all 0. So that means that x1 or x2 or xp is not equal to 0. A couple other things. Linearly dependent sets will occur if two vectors are multiples of one another, and if any set contains the 0 vector. So those are some things that we've talked about in the past. We now move to theorem 4, which says a set of vectors is linearly dependent if and only if at least one vector in the set can be written as a linear combination of the other vectors. For example, this set here is considered to be linearly independent because we can rewrite this set as a linear combination. So that is demonstrated here. So this section has these goofy examples again also. So I just took these directly from the text. I think that you can go ahead and read through these two examples rather than having me read them to you. But a couple things, basically, this set of vectors here is linearly dependent because it can be written as a linear combination. And then down here, let's see, this one here, because sine and cosine are not multiples of one another, then they're linearly independent. However, it gives an alternative example showing that this example would be linearly dependent. So go ahead and read through that. Now we have a definition that is referred to as a basis. Now this is going to come up a lot in your homework, so it's important that you have a pretty firm grasp on this. But basically, if H is a subspace of vector V, or a vector space V, then this set of vectors is a basis for H if these two things occur. So the definition of a basis applies when H equals V, and the basis of V is linearly independent And then down here it talks about when H doesn't equal V, what the consequence is. Some more examples directly from the text. In example 3, we have an invertible matrix, and it says the columns of A form a basis for Rn because they are linear independent and they span Rn by the invertible matrix theorem. The invertible matrix theorem is going to come up quite a bit in this section, so remember that theorem. I believe it is page 114. You might want to bookmark that. Then example 4, it basically talks about these different vectors, and the vectors are columns of the identity matrix, and this set is called the standard basis of Rn. And so this is kind of like the parent graph or the parent function. So let's look at this in specific examples. So the first thing we're going to do is determine if this set is a basis for R3. And then we're going to try to identify if it's a basis for R2. So what we want to do is we want to consider the matrix whose columns are the given set of vectors. So this matrix here. And if we row reduce this, now we certainly don't have to, but if we do row reduce this, we end up with this. And since this matrix cannot have a pivot in each row, so this matrix cannot have a pivot in each row, that means that its columns cannot span R3. So the given set of vectors is not a basis for R3. And that is super messy. I'm really sorry. Okay. Now let's talk about if this given set is a basis for R2. Now here, since V1 and V2 are not in R2, they cannot be a basis for R2. So that's pretty straightforward. Now, one thing I will mention is that V1 and V2 are linearly independent, so they are a basis for the subspace of R3, but specifically the span of V1 and V2. Let's look at another example. So let's evaluate this. We have these three vectors, and we want to determine if the set is a basis for R3. Now, remember, if A is invertible, then the columns of A span R3. And this is by that theorem, what's it called? The invertible matrix theorem. So again, the invertible matrix theorem, page 114, says that if A is invertible, then the columns of A span R3. So what we want to do is create a matrix A from these given vectors. which is this. And if we row reduce this, so, we take our time, figure out the row reduction, we end up with this matrix here. And we can clearly see that we have 3 pivot positions. Since we have 3 pivot positions, this tells us that A is invertible. And since A is invertible, the columns of matrix A form a basis for R3. And we are done. Okay, so in this example, we are given this set, and we want to verify that this set is a basis for Pn. And remember from previous sections, Pn is the set of polynomials of degree n. And this basis is called the standard basis for Pn. Okay. So knowing that Pn is the set of polynomials of degree n, we know that S spans Pn. And we want to show that S is linearly independent. If S is linearly independent, then S is a basis for Pn. So let's just kind of set this up a little bit. So let the following hold true. So x1 times 1 from the set plus x2 times t, x3 times t squared, so on and so forth to x sub n times t to the nth power. And this is equal to 0 times t. Now, this equation only holds true if every term, if every term equals 0. So if we want this equation to equal 0, if we are adding these items together, everything must be 0. Well, in order for that to happen, then x1 must be 0, x2 must be 0, everything needs to be equal to 0. This shows that S is in fact linearly independent. Dent. And that tells us that S is a basis for Pn. And we're done. We now have theorem 5, which is also referred to as the spanning set theorem. This is on page 212 in your text. You can go ahead and read through this. There are 2 things that are involved in this theorem. So just read it carefully and we will take a look at some examples. Okay, so here's our first example involving the spanning set theorem, and this example involves quite a bit, so hang tight here. We are given these 3 vectors, and H is the span of the set of vectors. It then goes on to say that V3 can be represented as a linear combination of the other 2 vectors. And we want to show that the span of this set of vectors is equal to the span of this set of vectors. And then we're going to find a basis for that subspace H. Okay, So we're going to take some baby steps here. So the first thing is I want to make a note. Every vector in span v1, v2, so every vector in the span v1, v2 belongs to H because we can represent this as a linear combination, namely x1 times v1 plus x2 v2 is the same thing as saying x1 v1 plus x2 v2 plus 0 times v3. Those are the same. Okay, well now let's take this a little bit further. Let's let C be any vector in H. So we are going to let C be x1 v1 plus x2 v2 plus x3 v3. Okay, easy enough. So it's some vector in H. Okay, well, now we know that v3 is equal to what I've circled in red here. So by substitution, if I take that and plug that in here for v3, then this becomes x1 v1 plus x2 v2 plus x3 times v3, but that is 5v1 plus 3v2. And then continuing with a little bit of algebra, I end up with x1 v1 plus x2 v2 plus 5x3 v1 plus 3x3 v2. Now, looking at this, I can identify some like terms. I have a v1 and a v1, and then a v2 and a v2. So I can factor out that those GCFs. So v1 times x1 plus 5x3 plus v2 times x2 plus 3x3. Well, looking at this, C must be in the span of v1, v2. So every vector in H belongs in the span of v1, v2. Okay, so we have just shown this piece here. Okay, so therefore C is in the span v1, v2. So every vector in H belongs in that span. Now, another thing, so to answer the next part, H and span of v1, v2 are the same set of vectors. Oops, vectors. So the set v1, v2 is a basis for H, since v1, v2 is linearly independent. And that's from theorem 4. And that concludes that example. Okay, so here This is a little bit different, but we want to find the basis for column B, where B is equal to this here, which is this matrix. Great. So looking at this, it's in echelon form, and we can identify the pivots here. And each non-pivot column, these guys here, is a linear combination of the pivot columns. Okay, and you know, you can experiment with that or analyze that if you want. So by theorem 5, the spanning set theorem, we can discard the non-pivot columns. And then the set with the pivots, so B1, B3, and B5 will then span column B. So S equals B1, B3, and B5 is equal to the set given here. And these are just the first, third, and fifth columns. So this is the basis for column B. Now, since, since B1 does not equal 0, so since this column does not equal 0, and no vector in S is a linear combination of the other vectors, S is a linearly independent set by theorem 4. So the previous example basically sums up this theorem here. So if you look at the previous example, it will help us find bases for two other vector spaces related to the matrix, namely null of A and column of A. So the theorem 6 here says the pivot columns of a matrix form the basis for column A, which is what we just illustrated in the previous example. So you must, this is super important right here. You must use the columns from the original matrix A, not the matrix in reduced row echelon form. So that is something that is important and will come up in your homework. So just be cautious of that. Here is a warning. The pivot columns of matrix A are evident when A has been reduced to echelon form. Be careful to use the pivot columns of A itself, which is what I just talked about. Row operations can change the column space of a matrix, so be very careful there. This concludes the lesson for section 4.2.